So thanks again for the invitation. Yeah, so I'll today talk about neural program synthesis, and as Marcus mentioned, there's also an interesting story about the group. I'll briefly talk about how it came about. And yeah, a lot of the work here I'll be presenting is with a lot of great collaborators in the deep learning team and cognition team at Microsoft Research. So before starting, I want to start with this observation, which is quite interesting, that I was thinking briefly, thinking about the progress we have seen in current deep learning successes, and thinking about how evolution works. If we think about how people, when they are born, when kids are born, they first start to see the world, how the things are in the world. Then they start talking about things, and then they start talking about things that make sense, just like language. So in the same way, we have seen breakthrough performances in computer vision. We have recently seen almost human parity in speech recognition, and now we're starting to get towards better at learning, at understanding language semantics and reasoning. So kids nowadays, after they learn how to talk properly languages, nowadays in modern generation they start programming. So here's my 3-year-old niece writing Python programs. So it's pretty natural. We should try to learn programs using deep learning. But more seriously, a lot of breakthrough performance we've had are mostly due to on tasks that are based on pattern recognition or classification tasks. Whereas if we want to go towards more general intelligence or to try to do richer things, we really ought to learn more algorithmic things, where there's not just one action to take, but a sequence of actions based on some condition. So in our group, we believe that one way to think about algorithmic tasks is in terms of programs, because programs provides us with abstractions, compositions, control flow, complex control flow. So if we are able to learn programs, we'll be able to actually train these machines to do much richer intelligent tasks. So as I was saying, we'll be able to do more things because programs are inherently more complex with more functionality. They also tend to generalize better as opposed to just training these deep learning models on some training data, because there's an inherent bias coming from the programming language. There are only certain programs that are possible. So that way they also tend to generalize better on unseen data. And finally, there's this concept of interpretability, that typically learned programs are going to be a bit more interpretable than low-level matrices we typically see in these deep learning systems. One can modify and edit, if they want, what the system has learned. So there are many benefits to training these systems to learn programs. So when we were forming this group about 2 years back, we had people from deep learning, programming languages, and reinforcement learning come together, and we were trying to write mission statement. What would it mean for the group to have success at some point? And as mission statement, we were thinking if we are able to build a system that can possibly win these programming contests, that would be a good stepping stone, a good way to see how much progress we are making. But along the way, so that's the long-term goal of training systems that can write programs for us. But along the way, the neural representations we'll learn for programs can be used for other things, as we'll see later on. Briefly, I'll touch upon. They could be used for program fuzzing, for finding security bugs, for repairing programs that are incorrect, and many other tasks like optimizations. So just to step back and try to think about what would it take to build a system that can basically write complex programs as right now humans do. So humans currently, programmers take some kind of specification as input in terms of examples, natural language, or partial programs. And then they're able to write code that is consistent with the specification. And to break it down further, there's typically some logic that needs to be used to solve the problem. And then it's not the case that we can just take any programmer, give them some task, and they're able to write the right program. It takes time. They learn different concepts. Maybe in the beginning they're not as good, but over time they get better and better. So our idea was actually, can we incorporate some of these steps about building a system that can take these kinds of specifications, write complex programs, and also be able to do logical reasoning, and maybe in the beginning it's not so good, but over time it gets better. So before getting into some of the systems we were developing, I wanted to contrast also. As I was saying, learning programs is actually quite useful, and we are seeing a lot of interest recently in the deep learning community in general, in specific. So there are many papers written nowadays on training these neural architectures for learning algorithms. One of the more famous one last year that appeared in Nature was this system called DNC, differentiable neural computer, where there's an LSTM controller in the middle, which has access to a differentiable memory to which it can give commands to read and write. And this whole system is differentiable because these are soft reads and soft writes. And given a task, let's say sorting a list or finding an element in an array, one can train such architectures. So I'll call all these systems neural program induction. There are other systems as well that instead of having memory, they have neural differentiable stacks. They have queues. The problem with these systems are quite a few. First of all, it takes lots of examples to train them, typically millions of input and output examples. They tend to not generalize more than on new inputs that are bigger than the ones on which they are trained on. Essentially, what's happening in these cases is they are trying to embed program semantics into the network itself. And inherently, programs are discrete. So there's a mismatch between trying to learn something that has different semantics than what programs are. And finally, they are non-interpretable in the sense, at the end, what you get back is a bunch of matrices with weights. It's hard to understand exactly what the system is doing. In contrast, in program synthesis, what we're going to look at is, instead of trying to embed program semantics in a low-level way into matrices, we're going to have functional abstractions. Like a program will have operators. We'll see, as we'll see later, since we are going to restrict the space of things the network can learn in terms of programs, they tend to generalize better because there's a prior coming from the language. It still has a problem in the sense where we still need lots of examples because we'll be training on one task. So you can imagine, let's say we want to train a sorting algorithm that in a language subset of C that has comparison, swap, and those kinds of operators. But still it's slightly better than program induction because you get back a program and you can understand what the network is doing. But in this particular talk, I'll focus more on this thing which we call meta neural program synthesis. The meaning will get a little clearer afterwards, but the main idea is we still want to learn, we want to train these architectures to learn programs over operators in a language, but the key difference here is that we want these systems to learn from very few examples, maybe 2 or 3 examples, a complex program. And we're going to use this notion of multitask learning in the sense we'll train these architectures on lots and lots of programs from some language in a given domain. And the hope is it really learns the semantics of the language to generalize to new tasks from very few examples. So I'll start with this first system we built for which we call neural flash fill. So do people know about flash fill from before? Great. I can give a small example where a flash fill is a system which allows users who are not really programmers to write complex. Do you know, Marcus, what happened? Or well, let me see. Oh, I think it's good. Yeah, great. So Flashfill is the system which allows users to do transformations inside spreadsheets or regular expression-based things without knowing, without having to know all the complex details about regular expressions. For example, let's say I want to format this number into some format like SSN. I can give a couple of examples. As soon as I start typing the next example, it learns a program that can, based on regular expression, that is consistent with the example, and the user can say, okay, this is fine or not fine. It can do more complex things. Let's say, want to transform names in certain way. Oh, sure. Sorry about that. Is this better? Oh, great. So yeah, so we can give an example, but you would notice here that it made a mistake. Second example, so I can say, oh, I don't want a space here, but I want a space here. And now the system has two examples, and then it learns a program that is consistent with the two examples. So we can do all kinds of data transformation using examples. We can also build more systems on top of it. For example, let's say I want to build a system on top of Flashfill to get data from websites. So let's say I have a list of stocks in some place, and then maybe I want to get some information at some other place. So let's say stock. I guess the zoom might be a bad idea here. So here the user gives an example of where the information is, and then they say, okay, the stock price is here. And now the system is going to basically first learn a program to go from input to URLs, similar to something what Flashfill did, and then learn another program to extract the data items that are relevant for this task from the examples. So in this case, actually, it was, yeah. Oh, I'll actually get to that more specifically. Yeah, I think, but you can think of it as basically.
Because to me, this is sort of just finding the pointers from one to the other.
Yeah. So actually, we'll.
We did that some times ago.
Yeah, that's a great point. Yeah, let me show slightly more complex. Yeah, maybe that. But yeah, you're right that maybe it will get clear when I show more details. Yeah, I can imagine. Yeah. So for example, let's say I have some data from currencies, and I want to get the currency conversion rate. This one might be slightly more interesting. So there are websites that give that information. So we can load the URL. So this one is complex in the sense we don't want any. So actually, first of all, the URL is interesting because it has to extract the right pieces of strings, substrings from the inputs. But then we don't want any data item. We really want, let's say 17th November. So we give an example of the data I'm interested in. So let's when it's learning, I'll tell what is happening. So first it learns a program to extract relevant data to produce the URLs. But then you would notice that the dates here are in a different format than the column. Right. So it learns a program to transform. Exactly. And then it learns a program again here that can do a join between two tables. Yeah, so it's doing, it's learning.
That you sort of show examples,
yeah.
What it should do, and then from examples it kind of repeats.
Yeah, so you can imagine if you were not giving examples, you can write a program to do such a thing. Right, it's just that it's automating that part. It's not letting, it's allowing people not to write a program, but give examples and let the program be learned. Yeah, yeah. But maybe that will get more clear. Yeah, when I talk about. Yeah, so for Flashfill case, actually, here's is a small programming language for those tasks. This language basically what it does, It has a concatenation at the top level. It can concatenate a set of strings. Every string is either a constant string or a substring, and substring has two parameters, left and right. And those positions basically are of this form. There's a regular expression, kth occurrence of a regular expression. So for example, let's say this was the task a user wanted to do. They gave examples, input and output. The program in that language would look like this. It would be concatenate four things, F1 followed by comma space constant, F2 followed by dot.
Now,
Yeah.
sorry, folks.
Oh, no, please,
But
please.
You know, 30, 40 years ago, the Lisp people, you know, the proving theorem, the deduction people,
Yeah, yeah,
had this kind of a system. And the idea was that you just set the goal as a theorem,
Yeah.
and then you negated that, and you went through basically logical rules.
yeah, yeah,
And you showed, and the
Yeah.
path as you went through these
Yeah.
logical rules gave you the program,
Yeah.
synthesis program. So I'm sure you.
yeah, yeah. So actually, there's exactly. Thanks for pointing out. So there's a large piece of work on. So the whole field, people. The way to summarize this, the term people use for that line of work is deductive synthesis, where the idea is you use proof to construct basically either negation or satisfiability proof of given specification. But typically. And so there was a lot of work in 70s and 90s and 2000. What happened was, yeah, exactly. First of all, you need complex theories to do proof reasoning in those things. And many theories, right, so we have good theories for certain domains like linear integer arithmetic. But as long as as soon as we go outside anything complex, let's say even string reasoning right now is not very well developed.
With that whole system was
Yeah.
the complexity.
Yeah, exactly.
It killed you. Yeah.
Whereas in these kinds of things, it's we call it as more inductive synthesis, where instead of writing a specification, yeah, exactly, full specification, here you can just give examples. You don't have to write full spec of what the program's supposed to do. No, but thanks a lot for bringing this. This is actually good to contrast. Yeah, but more generally. For more and more complex programs, there's some work still happening on that front, where people are trying to build new theories on data structures, but that is still actually on smaller programs and more simpler algorithms. But one guarantee you get there is that you get correctness guarantee, verification that it's correct for every input, whereas here the correctness is only that whatever examples user is given will be consistent. Yeah, but yeah. So in this case, F1 would basically be
It's very much like Lisp.
yeah. So that we'll get back to that point, yes, later. So it says substring. Basically, it says last word, and F2 is first character. So this is a program in the language that can do the task, but we don't want people to write this program. Given the examples, we want the system to generate this. So the philosophy, the general methodology we'll try, since we're going to train a system to do this, we'll start with a programming language. We call this DSL. Since we need training data to train the system, we're going to sample programs from this language, generate lots of training data, and build a system to learn that it satisfies that, and then we'll get a synthesizer.
How many data samples do you really need for this?
Yeah, so it depends on how much human knowledge goes into. For example, the system I'll show right now, there's no human knowledge that gets into it. So we need about 2 to 5 million examples. But this is a one-time cost, and I'll actually get back to.
You must be kidding.
So programs actually nice compared to images or videos, because here actually you can run the programs, you can execute them. And there's no shortage of data in the sense you can take a language, generate as many programs as we want. Like there's no shortage. So for example, I don't know if the font is legible, but here's a random program from the language which says, get the string between third alphanumeric up to end of the string, followed by get string from first colon and get first 4 characters. So it's a random program we can sample from the language. We can generate a random input string, let's say 5 of them. We can run the program and get the output. So basically we generated random programs, we generated random inputs, we ran the program, we get the output. So now this way we can get input output program pairs. We can go as complex as we want since nothing is stopping us. We can sample bigger program and more complex program. So our task is going to be, we want to train a system that is able to take the examples and predict basically the program that generated it. And you can also imagine, let's say, a small child who doesn't know anything about these things. They probably don't know about what words are, what constants are. It really has to understand just from these examples what really these symbols mean and what does it mean to.
What happens if you have a smaller training sample, let's say 100 or so?
Then you'll have to use different architectures. Yeah. So when we go to these specifically more neural network based systems, yeah, they are very parameter rich, so they need lots of data to train. Yeah. But then we'll need other systems, and it's not clear if they'll be able to learn anything.
Are you considering other systems?
So we did consider before going this way, but I think this one is just so much nicer that I will see from the results that it's actually a much better way to build these systems, right, compared to other ways. So the goal is going to be this: we train on synthetic data, and then if the system has really learned the right semantics and of the operators and how to compose them, when we give it real data, what users do in Excel on benchmarks, on input-output example, it should be able to come up with the right programs. So that's going to be our evaluation. At very high level, the way we're going to build the system is going to have 2 components. First component is going to take examples and put them in vector space. Some will call that encoder. And the second decoder part is going to generate the program in a tree structured fashion, like an AST, node by node. Yeah. So there are going to be 2 main components to this system. And the basic idea here is that instead of the approaches we saw earlier, where like in DNC, where the functions were embedded inside the network, the semantics, and we were doing gradient descent on it. Here instead, we'll keep the program separate. So you can think of programming language as a context-free grammar, and programs as basically derivations in the grammar. So one's naive strategy would be we can just start from the start symbol of the language and generate transitions, expansions. But the problem here is that it's not going to scale because there are billions and actually infinitely many programs in a language. So what the network is going to learn, network is going to guide the search. It would say at this point, this expansion looks most promising. So the network is going to learn a function that takes a partial program tree at any point, what the examples are, and it would return which node to expand and with what rule. And this process we can apply again and again. We'll take this tree as input now.
Your representation is the tree structure.
Yeah. Exactly. We'll get to the tree structure representation, but yeah. So we think of programs as trees,
Yes.
and trees are basically derivations in the language grammar. Yeah. And we can apply this process recursively again and again until we have leaf nodes that cannot be expanded, and then we get a program. Yeah. Now the challenging part is how to learn such a function f. We want to learn it from data. So there are 2 main challenges. How do we represent programs? Yeah, in this neural space, and how do we represent examples? Yeah.
How do you make sure that you don't regenerate this same program in this way? You seem to like always only unfold one node at a time.
Yeah.
And can it happen that you get to say like to a program you already refuted earlier?
Can you get to a state where you get to the same program that you had visited earlier?
Yeah.
Um,
Can it happen, or is it?
yeah, so that won't happen because you're building the program incrementally. So at any point you're adding a new node to your previous node. So
But if the neural network is always selecting,
yeah.
it might just select the same thing. Of course, that would be a stupid.
So the way yeah.
I mean, it's probably only it's only
Some test of sameness.
Right, but the way network will work is every time it will create a new node, so it would never have a tree with the same set of nodes before. So there's not going to be any backtracking here. It would
it always takes the tree from the previous iteration.
yeah, and then extends it. Yeah,
The tree from the previous round has only is a tree with like.
yeah. Let's say 4 nodes. Yeah, it would expand any one, and that's it. Yeah.
Each tree in this state is like an intermediate, not complete program.
Oh.
Yeah, it's like a partial tree.
Oh,
Yeah,
so
yeah.
Yes.
You remember a tree of trees?
Yeah.
So like in this your session.
So you can imagine encoding trees. Yeah, it's going to be a distribution over trees that would be encoded in vector space, and then the decision is going to be how to add a new node. And now your new tree becomes a new partial tree becomes the tree with the new node.
But you could have a situation that you have a tree,
Yeah.
let's say a big tree,
Yeah.
and the new I/O will represent one of those nodes previously. That, I think, is the question. So that's why you need some test whether you have a previous node that matches your new I/O.
So I/O are going to be fixed for any task. Yeah, it's like a one-time thing. Only thing this will change across.
I/O is in real time.
Yeah, is the example. Yeah.
These examples are coming in.
So they all come together. Yeah, like it's not dynamic. It's like one time.
It's not dynamic.
Yeah.
Sorry.
Yeah. Basically,
Understood.
it's a one-time thing.
So
Yeah.
It's one time thing.
Yeah. So the task is.
When you said that you do the training in 100 times or 1,000 times,
Mm-hmm.
then the I/O is different every times out of the 100 times, 1,000 times.
Yeah. So the thing is, for this function, every I/O. So let's say the program has 10 nodes in it for a given I/O. So that would create 10 training points. That would say for every program with let's say 8 nodes, the program with 9 nodes would be one training point. So those 10 examples would share the I/O, but the others will have different I/Os. Yeah. So for every I/O task, we'll have as many training examples as there are nodes in the tree. Yeah, but we can also take it offline. Actually, yeah, I think it's an interesting discussion. But the idea is that every time we are building the tree, like adding a new node to the tree, so we're not going to revisit any tree. Yeah. So at high level, the question becomes how do we take a tree and put them in vector space? And the basic idea is that we can think of programming language, as I was saying earlier, as a context-free grammar. For every symbol, we will have a vector representation. For every rule, we'll have another vector representation. And then we'll have 2 sets of neural networks for every rule. And I'll show why. So let's say this is our partial tree for the time being. We first assign the leaf vector representation for every leaf. Then we use the first set of neural networks for every intermediate node in the tree that takes children representations and computes the parents representation. It's like a function that takes children's representation and computes parents. It keeps on going up. At the end, we'll get a root representation. Yeah. So at the end, we'll have a root representation. This is actually quite standard. People call this recursive neural networks as well. People use in natural language. But since we have to make decisions at the leaf level, so instead of stopping there, what the network does, it now uses a second set of neural networks for every rule. It takes a root representation and it computes children's representations from the parents, essentially. So at the end, we get updated representations for every leaf node. And now actually we can basically multiply each leaf representation with the rules representation to get a probability of every action, every expansion we can take. And we can just do a softmax over all the actions and say which one is the best at this point. So we use this architecture, and now since we have the ground truth saying what the program should be at every point, we can just do a cross entropy loss to optimize this function and then train.
Where are the Z's? You have a softmax.
Yeah, Z is basically just a multiplication of updated leaf representation after the reverse pass. Yeah, with the vector representation of a rule. Yeah.
It's a dot product.
Yeah.
Okay. And phi is, I see.
Phi is basically, yeah, just the reverse. Yeah, on the reverse pass.
Okay.
And the original phis are initialized randomly. During training, we'll learn phis and omegas, yeah, and the W matrices. So from the data, so this is actually basically the way to encode any partial tree in vector space, and then choose the most promising leaf to expand, and with which rule, yeah.
So you create this space of Z's, and then you look for soft, which is really a max. You look at some kind of optimization.
Yeah, so at any tree, you will get a distribution over all possible expansions, and we try to optimize the distribution to map as close as possible to the ground truth we have. The ground truth says which leaf is expanded with which rule. Yeah.
What's omega? Omega of R in the
Yeah, for every rule we have a vector representation in the grammar, which
R
is
the rule.
R is the rule. Yeah, yeah. Or maybe I guess, yeah. R is the rule. Yeah.
Sorry, I was confused. I thought it was the root, not the rule.
Oh, sorry. Yeah, I guess I should use another term, but yeah, R is the rule. Yeah.
Wait, what is the ground truth system? You could have multiple leaves that need.
That's an excellent point. Actually, I was avoiding that. It's a little more technical, but basically you could have the ground truth basically has multiple leaves. Every leaf has to be expanded. That is non-terminal. But what we say is that some rules are, but every leaf is going to have a set of rules. Not one of them is going to be chosen in the ground truth. But we are letting the system. We're not telling the system that always choose the leftmost first. So the intuition here was that even when we are programming, it's not clear. We always start with like writing the program from top to end. We sometimes write middle part of the code. So maybe we want to write something here and then get back to here. So we wanted to have this flexibility and not impose a constraint that always expand the leftmost thing. So the cross entropy loss would say any one of them is okay. So the loss function would say all of them are fine, which are in the ground truth. And anything that is not in the ground truth, any rules that are not present in the program would be bad, zeros, yeah. Yeah, thanks. So I'm actually running a little late in time, Marcus. How much time do I have?
We still have 15 minutes.
Yeah, so I'll try to speed up a little bit, and then we'll have a discussion afterwards. Yeah. Oh, great. Yeah. So basically, I'll speed up a little bit, but let me know if there are more questions. So we have a generative model for trees now, but now we want to condition it with examples. And one basic way is to just basically we have input output strings. We can run LSTMs over them, get the combined representation, and use it as an additional input to the leaf nodes when doing up and down passes. We can also do a little bit more fancy encoders, but that's not that interesting. So here's the results, essentially showing that up to programs of size 13 nodes, this model actually does almost perfectly. Another point about programs compared to, let's say, image recognition tasks is if we make a prediction there's a cat, there's nothing we can do about it. We have to say, okay, there's a cat. Whereas in programs, if we predict a program that is not wrong, that is not right, if the program is not consistent with the examples, we can go back and say, give me the next best program. So here you will see things like 100 sample. That means you can get top 100 programs from the distribution and check if any one of them is right and return that back to the user. So this works very well up to programs of size 13 on synthetic data. And when we take it for real for flash-fill programs as well, it works quite well. About 85% of the cases it does well, where the programs that are needed for those tasks are up to size 13. Programs that require larger size, yeah. So this particular network can't do, because training dynamic trees, especially at that time, was very difficult. We were using static computation graphs, and we could only do batching of programs up to size 8. Now we are trying out new architectures that can do larger batching. But yeah, the R3NN network is actually something for programs. It's actually quite useful to have context to make any kind of predictions, which we are exploring more later. So what happened after that was we took a step back and said it's hard to train these architectures that are tree structured, that are dynamic in different sizes. So how about we make our decoder more of a sequence as opposed to trees? So one can think of this program synthesis task as a sequence-to-sequence task, where I have 3 sequences. I have input string, output string, and a program. And program, I can linearize the tree into a set of sequence of tokens. So we can have a basic model that basically runs an LSTM in this fashion, where the hidden state of output is initial state would be last state of the input LSTM. We can add attention, different kinds of attentions. We can have program LSTM attend over output, program LSTM attend over input as well. And we can use bidirectional LSTMs. So there are many variations we can have in sequence models. Another interesting thing is, so this works for one input example. What happens if we have multiple examples? And the intuition there was we run multiple LSTMs for every example with the same set of weights. We get some hidden representation of programs, but instead of pooling right at the example level, at every timestamp we take the predictions for every example and we do pooling then. So it's more like, intuitively you can think of them as doing intersection. We want programs that are consistent with all the examples. So for example, if first input it's saying it's some other regular expression, but all the other inputs are saying this is that regular expression. So intuitively the network would pick the one that is majority, or that has the maximum probability. So the nice thing was sequences were easier to batch, even though they're less expressive than trees. But it worked so well that we added even newer things to the language, new operators, and it still performed really well. So when we look at the flash fill test, this accuracy of this particular model went up to 92%. Whereas the previous handwritten system in flash fill was about 89%. So it already was quite surprisingly even more accurate and than hand-coded version. Another interesting property of learning a system using these networks as opposed to hand-coded rules is that they can also tolerate noise. So for example, if we make spelling mistakes in the examples, these networks can still have relatively good accuracy, whereas since the hand-coded system are sound, any kind of noise would say I cannot find a program that is consistent. Yeah.
Why doesn't Excel, the normal system, just go directly down to 0 with one noise?
Yeah. So actually sometimes since we are doing random noise injection, so some noise doesn't really matter. So let's say I want to extract city name from some address. I'm injecting noise in other parts. Yeah.
Okay.
So I talked about, as we were saying earlier, this looks like a Lisp language. So a flash fill, you can think of it a functional language that has basically a composition of functions. So that's what we started with, to see how easy or hard it is to train architectures to learn them. Then actually now we are looking at a little more complex language that has control flow, loops, and conditionals in it. It's called Carol. I'll talk briefly about it. At the end, we want to go all the way to programs that also have variables in it, stateful variables, and that can read and write to memory using variables. So we talked about example-based specifications. Another benefit of having neural models is that we can encode other kinds of specifications as well, maybe natural language or partial programs. So we have a system we are building where users can actually, instead of giving examples, sometimes give natural language commands saying, give me the total of this column, or which country has the maximum population, those kinds of things. And that would be the input, and output would be a Excel program. So just briefly talk about Carol. Carol is this language which is taught at Stanford Intro to Programming class, where students are given test cases like input, output, and they have to write a small program. In this case, it would be, basically a small loop that says put marker. Yeah, so program is supposed to take input and create output world. And then they have typically 3-4 examples.
So what does it mean? You take the input, which is the robot,
Yeah.
and it's supposed to lay down on one of those those purple circles. Is that the task?
Yeah, the task is to, so Carol actually has a fixed world. You cannot create new variables, but you can modify the world by putting and picking markers and using some kind of control flow. So in this case, the task is there's these grids, and the goal is to produce an output where the markers are in these positions. Yeah. And that's like a small program to do this task. Yeah. But the programs can get more complex. Here's the complete language. It's supposed to be Turing complete, but it has these control flow like while, if statements, and then certain set of actions. So for this task as well, we use the same strategy as I was talking earlier. We sample programs from the language, we generate training data, we train these architectures. The only difference is, instead of using LSTMs for encoders, since we have these pictures of test cases, we use CNNs to encode these input and output.
The news channels, yeah.
Not the fake news, the convolutional networks, the real news. Oh, I should not say that on the camera. Okay, but yeah, the CNNs are basically convolutional networks that we encode the pictures, and then we use LSTMs for decoding. And actually, it works pretty well. It gets about 72% accuracy on supervised learning. One interesting property here was that since we're doing supervised learning, basically we are forcing the network to always produce the program that is there in the training, whereas there can be multiple programs that are consistent with the examples, since examples are under specifications. But we are still forcing the network to produce the same program. So the basic idea was, instead of using the supervised learning metrics saying program has to be correct token by token, we can use a metric that says any program is fine as long as the output is consistent. So that's where the reinforcement learning comes in, because executing a program is non-differentiable. It's a discrete operation. So the basic idea is, we first start with supervised training. Then we sample program from the model. We run the program on the examples, and we give a positive reward if the output matches. So it's a simple reward function. And using the reinforcement learning, it got about even 6 to 7% more improvement on accuracy. And then we also wanted to see, can we take the Stanford class test, what students take, and see how well it does in that. So we took last year's exam, and this particular model got 7 problems correct out of 16, about 43%, which is about, the instructor said we'll get grade D, which is better than failing. But we want to improve that number, a little more. And interestingly, one of the class test problems were like this. They had to go write a program to do this from this. And surprisingly, the system was able to write this program, which is quite complex. The other techniques in the past, like sketching or constraint solving, don't scale to problems of this size. So it's pretty interesting that these networks are able to write such large programs. But more going forward, we are looking at techniques to combine symbolic approaches like constraint solving with these statistical approaches to see if it can be scaled even further. So instead of writing the full program at once, can we first get a sketch of the control flow using these statistical approaches and then use symbolic approaches to fill those gaps? So very briefly, I talked about program synthesis. That's the longer term goal we want to get to. But in the meantime, there are many other applications that can be enabled by these program representations. One of them is fuzzing, where fuzzing is basically this idea that we want to test programs for these security bugs. It's a very simple technique. You start with a good input, you do random mutations, you run the program, you find crashes, and you do this again and again, millions, billions of times, and in the hope that we'll find a crashing input. And this is actually one of the reasons why, it's been quite successful at Microsoft. We don't have any of these bugs anymore, the blue screen ones. So it's pretty useful, and also outside Microsoft, pretty much in general, it's been quite successful. This simple idea. Google has the system called AFL, which basically mutates the inputs and uses the feedback to have a better strategy on mutating the inputs. So one of the things we tried was we took AFL and we wanted to see, can we learn a policy that says that given an input file, what bytes are more interesting to fuzz than others. So in the beginning, it starts doing random mutations. It starts looking at what coverage the mutations are getting. Over time, it learns that certain bytes are better than the other by basically encoding the window of bytes and learning attention over which bytes are more interesting.
What is the fuzzing? Is it a random combination or?
Yeah, it's like mutations. Yeah, random mutations to well-formed inputs. Yeah, and it turns out, when we learn such a policy, it's able to cover even more instructions and actually many more crashes. AFL didn't find anything in 3 days, whereas our system was able to find many crashes for some inputs. Another thing is actually, since we were doing grammar learning in the synthesis thing, another usefulness of learning grammars is for fuzzing. So if we do random mutations on complex formats like PDF, very quickly it would become an invalid file and the parser would just discard it. Whereas here, and typically what people do, people write grammars by hand for fuzzing. But for formats like PDF, it's almost impossible because it's over 1,300 pages long. It's quite difficult to write a good grammar. So we trained these models, generative models, that given thousands of PDF files, learn the grammars, some representation of grammar of PDFs, so that we can generate new files that look like PDF and are not trivially invalid. And surprisingly enough, these sequence models were able to learn quite complex PDF grammars and again result in better coverage. So finally, another application again of these neural embeddings is giving feedback to students on online courses. So typically when students go to these MOOCs classes, there are more than 100,000 submissions for every problem. Many of them are correct, many of them are incorrect. So we can take all the correct problems and learn a language model-like thing by training these program representations, such that in future when a bad program comes in, the model can go in and say, this part of program looks suspicious, and this is what the system, what the suggestion is to fix the program. And then we can do some symbolic reasoning on top to make sure the suggestion is really correct and find modifications that make it pass all the test cases. So in summary, I think this is an exciting area that's just getting started of building these machines that can write programs of different complexities. The longer term goal is actually to see how far we can go all the way to write programs all end to end. But along the way, we'll see that these program representations are also useful for other analysis tasks like program repair, fuzzing, and optimization and other things. So thank you for your time. Yeah.